Thanks everybody for joining us. Today we have Jenny Smith, who's a AOE grad student working on her PhD and going to talk to us about some neat things about high altitude balloons. So without any more introduction, over to you, Jenny.
Great, thanks, Kevin. So yeah, my talk is going to be probably more of a high-level talk than some of the past talks have been. But I'm talking all about high-altitude balloons. So let me go ahead and go to the next slide. Yay, it worked. Okay, so my presentation today is all about balloons, and it's not these kind of balloons, although these kinds of balloons are exciting. And you know, it's probably a bad idea to release this many balloons in the environment because it's bad, but won't be talking about these. And I wish I was talking about something like this. This is a cartoon from the 1900s about what they imagined life would be like in the year 2000. And this would be a river crossing or some water crossing. Instead of having ferries or things, people would be supported by balloons. So I wish I was talking about something like this, but unfortunately we don't have that. Instead, I'll be talking about high altitude balloons. And there are a couple different types, and I'll go into that later in the presentation. But yeah, these are the kind of balloons I'll be talking about today, and the research that can be done, and a little bit on the history. So just, I guess, a brief outline of what I'll be discussing. I've already kind of mentioned, but I'll be talking about what are high altitude balloons, a little bit of the history, what are they used for, why do we care, and then go a little bit more in depth, looking at the different governing equations, because each of the balloons have different dynamic models. That's important for the predictions when you're planning a mission. I'll talk a little bit about where the atmospheric data comes from for these predictions and this mission planning, some of the challenges, the biggest challenges that we faced in making these predictions, and then finally I'll conclude stepping back out, looking at the big picture and why all this stuff is relevant to me, to Virginia Tech, and then in general, some of the cool work that I'll be doing for my dissertation, and hopefully will help other ballooning people. But I'll start this presentation with a brief intro for my background in ballooning and why I'm interested. High altitude ballooning is a little bit of a niche thing. So my interest in high altitude ballooning, or HABs, H-A-B, high altitude balloons, started when I was 7. I tagged along to a project that my parents were doing called Big Blue, which was the Baseline Inflatable Glider Balloon Launch Unmanned Experiment. It's a mouthful. But essentially what the project was, it was to test the performance of an inflatable rigidizable wings in high altitude conditions. And they were investigating the feasibility of flying on Mars. So this project was the first project that I saw that introduced me to using HABs, or high altitude balloons, as a platform to rapidly test novel design ideas in a space analog environment, in this near space environment. And in this case, for this project, that near space environment is the closest thing on Earth that we have to Mars's atmosphere. So since then, since I was 7, I've been a part of many different balloon launches, including imaging the 2017 solar eclipse. You'll see a few images from that experience throughout this presentation, actually. And then those ballooning experiences that I've had since the age of 7 through my undergrad career have inspired my dissertation topic, which I'll mention a little bit later, but it's all about balloons and planning balloon missions. You can see that's me at one of the projects for the Big Blue projects out in Colorado. So diving straight in, just a little bit of history in balloons, where they came from. So in June of 1783, Montgolfier, I'm not pronouncing that right, sorry, successfully conducted the first hot air balloon flight. And pretty soon after, I think that year, there was another person who did it in Paris. And based on those historical sources, it reached an altitude of about 1,900 meters. So after those successes, manned balloons, like hot air balloons, were developed with using both hot air and hydrogen, mainly just for fun. However, there was a scientific aspect that they were used for. So they were used for meteorological observations, and they were also sometimes used for military purposes, for surveillance, among other things. So these systematic observations, especially in astrophysics, actually really started around the late 1800s, which is about 100 years after those first hot air balloon flights. And those particular flights really opened up the era of performing space science with balloons. And the first main science mission that was conducted using balloons was actually the discovery of cosmic rays by Victor Hess, and it was on board a balloon in 1912. And so those observations actually confirmed the increase of radiation due to altitude. So since then, most of the scientific discoveries were completed by manned balloons until the early 1900s, or about the 1940s, where balloon systems were revolutionized by using new plastic films and telemetry systems. These new balloons could carry payloads of several tons and attain altitudes of up to 40 kilometers. And then by the 1960s, actually several balloon launching stations have been established in various countries around the world. During this decade, so the 1960s, 70s, 80s, the predecessor to the NASA Ballooning Program Office, which is NASA's ballooning program for large scientific balloons, was established in the 1980s as the National Scientific Balloon Facility, the NSBF, in Texas. And these large balloon flights with heavy payloads still actually had a pretty low reliability, probably around 50% success rates, which is right around when actually the NASA Ballooning Program Office was established. And some of the first work that they did is they implemented a balloon recovery program, as well as qualified designs, test programs, and film qualification standards in response and trying to fix the reliability issues of the large balloons. Ever since then, the rest is history. So long duration ballooning especially has assisted in both Earth and other scientific observations. Most of that is about large balloons, but in the time, you also have the smaller latex and mylar balloons that have been developed. And I'll talk a little bit more about that in the next slide. So this last thing here, you can see, so on the left, it was in the 1840s to the 1950s. And then even this year, NASA is planning on launching one of the largest balloons ever launched for the longest duration flight with a cosmic ray catcher. So yeah. So today, what are high altitude balloons used for? And the popularity of high altitude balloons has fluctuated throughout history, but especially recently, there's been a significant uptick in the usage for many reasons, but primarily the miniaturization of technology, which enables taking higher fidelity measurements with smaller instruments. And these balloon platforms can support many different types of payloads. So you have atmospheric science, astronomy, surveillance, satellite system prototypes, et cetera, et cetera. The list goes on and on. Just some examples are here on the slide. In the upper left-hand image is a NASA ultra-long duration balloon, which is supporting a Gusto mission, which is a spectroscopic terahertz observatory. In the middle, they also a lot of bio experiments. NASA performs a lot of biology experiments because that near space environment is the closest thing on Earth to Mars' atmosphere. They sent some microbes up to the edge of space to see if they could survive, looking at cross-planet contamination, especially when we're exploring new worlds. And finally, in the bottom right, you see an example with the Google Loon project, which aimed to bring internet to places that couldn't be necessarily supported by satellite or cables as it is traditionally. So the primary benefit of high altitude balloons is that they can reach altitudes up to 120,000 feet, which is about 40 kilometers. And that brings the payload to the edge of space. And so the near space environment, it's ideal in addition to all of these other reasons, it's ideal for testing and validating novel space technologies at a very significantly lower price and a shorter development time than, say, a rocket launch. You get hours to weeks to even months on the ultra long duration balloons versus the couple minutes you might get off of a rocket launch. In addition, high altitude balloon missions, you have a much higher probability of equipment recovery, which can allow for further development of that hardware that now has flight heritage in a near space environment. So why should we care about balloons? And why do I care about balloons? Well, it's an incredibly cheap environment, actually, that is essentially space that you can exist there for extended periods of time where no other vehicle can actually support missions. And in addition, there are very few examples, and what I'm interested in are ballooning constellations, like the Google Loon project, that can be utilized and be examined for other purposes like atmospheric sensing or validating new satellite concepts, satellite heterogeneous constellation concepts, and the new technologies being developed for those efforts. So based on the idea that there are a lot of unexplored opportunities in balloon constellations, that kind of leads to what my dissertation research is. And the primary objective of that is to integrate high altitude balloons into Discotech, which another student developed for her dissertation work, which is a mission systems optimization tool. And this will enable planning multi-balloon missions, so like Google Loon, or for other objective purposes, and then being able to evaluate the feasibility of those missions themselves. In addition, the tool will enable mission planning for cross-platform optimization, so between satellites, balloons, and ground stations. You can look at, say, wildfire detection and monitoring. The satellite passes only so often, or you get one satellite. Can you put up a balloon to help increase your aerial coverage? And how would you go about doing it? What would be the cost of going about doing something like that? So that's what I'm looking for in my dissertation, and why all of this information about high altitude balloons is relevant, at least to me, and is relevant to the scientific community. So the rest of this presentation actually focuses on kind of a high-level introduction of balloons. So what are the different types of balloons? What are their governing equations? And how are the governing equations a little bit different? And then finally, the challenges with predicting balloon flights. So diving straight in, there are two general classifications of high altitude balloons. You have the free flying balloons, which are pictured on the slide, and they do not have a propulsion system. And then you have powered balloons, which are also known as airships, that do have a propulsion system. So think blimp, essentially. So for the remainder of my talk today, I'll be focusing more on the free flying balloons, which are the primary focus for my dissertation work. You have three types of balloons. You have on the left-hand side, the latex balloon, which typically carry payloads up to 25 pounds. The flight duration is about 3.5 hours. These balloons, you launch them, they ascend to the particular altitude where the latex balloon bursts, and then the payload string descends under a parachute uncontrolled. Usually these balloons average altitudes of about 110,000 feet. They've been known to get higher, and they've also been known to pop lower, depending on how much your payload weight is and if there are any defects in the balloons themselves. On the right-hand side of, or I guess in the middle on the right-hand side of the slide, you have the zero pressure and super pressure balloons. Both of these balloons are typically made of polyethylene plastics. They can lift payloads up to 3 tons, and the max altitude depends for these balloons, but usually is somewhere between 60,000 feet and 130,000 feet, depending on the payload and the mission basically desires and the requirements for the mission. So to differentiate between the zero and super pressure balloons, zero pressure balloons that here in the middle of the slide typically have open ducts about halfway down. In this case, here are some of those open ducts that allow the lifting gas to escape, so burp, as the balloon ascends, which reaches a maximum. As the balloon reaches its maximum volume, it basically slowly equalizes to the pressure, and then typically zero pressure balloon flights last somewhere between a few hours to a week, whereas super pressure balloons, unlike zero pressure balloons, super pressure balloons are completely sealed, and they're often referred to as the pumpkin balloons, and you can see on the right why they would be called pumpkin balloons. And their missions typically last anywhere from 4 hours to a month plus, depending, for the ultra long duration balloons. just to give you a little bit of an idea of the environment they might fly in, on the left-hand side, you have temperature, and on the right-hand side, you have pressure. So here, weather balloons typically fly in the stratosphere. They go from the troposphere through the tropopause, and then they get into the stratosphere. And in that case, the lowest temperatures they see, at least in standard atmosphere, is -55°C. And then typically a lowest pressure of around 250 pascals. This will vary depending on what altitude you're at, depending on the season, which is why there's a note on here that actually using the standard atmosphere assumption for your predictions isn't the best assumption, and can significantly add uncertainty to your predictions. So while this is nice for talking purposes and presentation purposes, standard atmosphere isn't the best information to use when you're doing balloon predictions. So one of the primary features that defines a free-flying balloon is that the balloon and or the parachute and flight string is not controlled by a propulsion system. And due to this uncontrolled ascent and descent, one of the most important aspects of a high-altitude balloon mission is predicting the balloon's trajectory to protect the public and the payload. There are FAA regulations that define operating limits for unmanned free balloons, such as the balloon cannot launch or land near a populated area or in an area where the payload creates a hazard to people or property not associated with the project. And having an accurate trajectory prediction is imperative to help determine the mission's regulation for the compliance for the mission regulation for FAA regulations for launch and landing locations. And often the decisions for the targeted launch date and suitability of the predicted landing location are made purely based on the projected trajectory, which significantly affects the mission. So a little bit deeper to talk just a few differences about the governing equations between the different balloon types is for latex balloons, you have your standard for vertical motion. So this is your altitude calculations for the predictions. You have MA equals F, right? And so on the left-hand side, here's your M, there's your A, and then this is your F. The FBD for balloons are pretty simple in the sense that you have buoyancy going up and you have weight and drag pulling down. In this case, for the latex balloon, you can see imaged right, the buoyancy is going up and you have the weight of the payloads and the drag of the balloon going down. In this case, the total weight for the latex balloon system is just going to be the weight of the balloon film, so the latex balloon itself, the weight of the payload, the parachute, the flight string and everything, and then the weight of the lifting gas. For horizontal motion, because latex balloons are so small, you can make an assumption that that simplifies the equations, that they move with the parcel of wind that they're in. So in that case, when you're looking at horizontal motion, you're predicting horizontal motion, all that really matters is that you have the wind speed and wind direction from your prediction sources, from your wind atmosphere predictions, which I'll mention in a bit. On the bottom right-hand side of the screen is a very pretty flight day launch that we have. This was not a prediction, this was an actual flight that was recorded. So it launched here, it actually went up to an altitude, it burst at the start, and then it came back down. Between the launch and landing site, it was about 1.5 miles distance, to give you some scale here for this flight. I will say from my experience and from other ballooning experiences that this is a very pretty flight track, especially for latex balloons. If the wind isn't going in one direction and it's not in the season where the winds turn, then you can have, this was launched in Kentucky and we've had to drive to Tennessee to recover it. So you can have long recoveries in some seasons versus very short recoveries in other seasons. So looking at zero and super pressure balloons and the governing equations for this, you'll see it's very similar to the latex balloon, but there are a couple extra considerations that you have to keep in mind. So for vertical motion, you still have your MA equals F, your MA equals F. You still have buoyancy, you have weight, and you have drag. However, you have this, in this gray term, this ballast extra weight for zero pressure balloon flights. And I'll explain in the next slide, you'll see a little bit about why the ballast is important. But basically the ballast helps regulate the altitude that the balloon is able to float at during its flight, especially if it's a day-night flight cycle. It's a multi-day flight cycle. In addition to this ballast term that you have for the zero pressure balloons, for both zero and super pressure balloons, you have to take into this virtual mass consideration. And it's kind of, weird that it's called virtual mass, because it's not really a virtual mass, it's a physical mass that's being added to the system. But this virtual mass term is actually accounts for the mass of the air that's being dragged along with the balloon during ascent. And it's from the idea that it's caused by an accelerating body submerged in a fluid. Typically, this coefficient of virtual mass, the CM here, ranges between 0.25 and 0.5, but it changes. So especially for zero and super pressure balloons, the shape of the balloon changes significantly during ascent and during float and then during descent. So you can't just assume that it's always going to be a perfect sphere and use that for your drag model. Understanding the actual shape of your balloon significantly impacts the drag and the volume of your balloon for these calculations, both in the vertical and horizontal. So in addition, like I said, for the latex balloons, you can make the assumption that it moves with the parcel of air. You cannot make that assumption for zero and super pressure balloons. The balloons are large enough and the payloads are heavy enough that you actually do have to take into consideration a relative velocity, and the relative, especially in the drag term, the relative velocity of the balloon and the surrounding parcel of air. And I didn't include those equations, but they're looped into this drag term here in the drag X and drag Y. In addition, latex balloons typically neglect the idea that there's any thermal interaction happening. The predictions have been proven good enough without thinking about thermal effects. However, for zero and super pressure balloons, thermal effects are really important when you're making these multi-day predictions, especially because you're going to have significant changes in temperature, in pressure, and other things, especially when you're going through the day-night cycle. So on the right here, you can see a few of those sources for the temperature things that are being considered. In addition to this, you have to think about whether there are clouds reflecting light or whether there are no clouds. And that there have been some works of literature that have actually proven just how significantly whether there are clouds below the balloon or not actually change the flight and the altitude that the balloon is able to operate at. So those are just a few differences and similarities between the governing equations for the balloons. This next slide just kind of helps solidify the differences between your zero and super pressure balloons. Your zero pressure balloon is going to be on the bottom and it's going to have the significant variance. And during the day, you'll vent a little bit of gas basically to help keep the altitude, your float altitude constant. But during night, you're going to be dropping in altitude due to the pressure being lowering and everything cooling down. And so you're actually going to drop in some of that ballast. And so then that'll help your buoyancy go back up. And at some point, because you have a finite amount of ballast, you'll have to cut the balloon down and your flight will be limited by the amount of ballast you can bring for your payload versus the super pressure balloon, which has much less altitude variations during its flight. So another important aspect besides the governing equations is actually where the atmospheric data is coming from for predictions. So there are two categories here for where wind data and temperature data and other atmospheric data comes from. You have predicted wind data and predicted data, and then you have historical data. So typically your public path prediction tools, especially for latex balloons such as HAB or Astra or Michigan's Flight Planner prediction page, they use predicted wind data from the Global Forecast System, GFS, provided by NOAA. And some of them include even higher fidelity models such as the Rapid Refresh, which is another NOAA prediction tool. However, weather is predicted only 1 week ahead, has very limited accuracy, and even about 24 hours before launch, it's considered accurate with the air quotes, because even that can change. So, and the confidence of those forecasts actually changes with the season. So therefore, these like public trajectory prediction tools, they really only predict paths for up to 1 week in advance maximum. So if you're looking at planning a mission for the 2024 solar eclipse, right, you're not going to have weather predicted data out there yet. So that's when you use this historical data, which can give you maybe a glimpse at the trends that you would expect to see your balloons to travel during that particular event during that season. And it can help give general insight into like planning purposes, such as reserving hotels or equipment storage, things that would, be in the general area, but you can't necessarily pick out the launch locations for the day of 3 years in advance. You can have ideas, but it depends up until about that week before you can start solidifying what those ideas might actually be and the best place to launch would be. So in the dynamic models and in the predictions, there are a lot of the places that uncertainty is actually happens. So I've mentioned there's a lot of uncertainty in the forecast, just in general, but there's also uncertainty built into the forecast resolution, both in space and time. So it's not guaranteed that you're going to have predictions for the exact time when you're flying the balloon. So you have to be able to interpolate between not only spatial resolution, but time resolution for the model data. Also, in the seasons with high variability, especially in the months, I would say April and August, when the winds change, the accuracy of even those forecasts decrease, I would say pretty significantly. In addition, for the historical data, you have uncertainty in the measured data, which is inherent to the physical instruments themselves that are taking that data. As I mentioned, there's uncertainty in the balloon dynamic models, which mainly stems from the fidelity of the model that you pick. So for example, assuming that a spherical balloon geometry for a zero pressure balloon, when the zero pressure balloon looks more like an ice cream cone, it's not a sphere. In addition, including thermal effects, they have a significant impact on your predicted trajectory, but if you decide to neglect them, you're going to have a significant amount of uncertainty in your actual prediction, and it's not going to be a good prediction for you. There's also, that kind of all leads into predictions of the drag model, which is one of the most, there's been a lot of work done recently, especially on how to more accurately model the drag that especially some of these larger balloons experience during flight as it goes through the tropopause, especially, which significantly changes the coefficient of drag for the large balloons. There also is general uncertainty due to unpredicted faults. So that's kind of a catch-all uncertainty, which includes faults such as manufacturing defects, unexpected software bugs, off-nominal performance that could significantly affect the balloon's trajectory during flight itself. So for example, you overfill the balloon, so your ascent is going to be much faster, and you're probably, for latex balloons, you're probably going to burst sooner. Your balloon is going to burst sooner. And so then you're going to come down much sooner, and you're going to be in a very different location than you would expect if you underfilled the balloon versus overfilling the balloon. And then especially for latex balloons, again, the descent aerodynamics, you assume some kind of coefficient of drag, but when the balloon pops, and you can see down here in the bottom left-hand corner, 2 pictures from actual latex balloon flights, there's a high likelihood that the neck of the balloon, which is the part that the flight string is attached to, and some part of the balloon itself, so you see these strips of latex, will actually descend with the flight string and the parachute. And so that added weight from the neck and some percentage of the balloon, you don't know what that is, can be a significant weight added, especially when you have lighter flight strings, like 6 pounds. It can be a significant percentage of that actual weight coming down. In addition, the streamers, so you can imagine these acting like streamers as the balloon and the parachute and payload are falling. It can act as a sail. So if you catch the jet stream and it's moving really fast, it can push you way off track for where you expect the balloon to land and put you in some place that's maybe not the best, or put you in a big forest that's harder to get to than the farming fields that you were aiming for originally. And it also, the line can swing down and can inhibit your parachute from opening the whole way. So that changes the coefficient of drag and it brings it down. And all of these uncertainties significantly play into your trajectory predictions and when you're trying to even plan this flight. So a part of this work has more recently, there's been a focus on this and trying to quantify the uncertainty, especially due to the atmospheric data and also looking at the dynamic model uncertainty. On the right here is actually an example pulled from one of these works that I'm going to be looking at, or I am looking at, which shows the probability swath for a super pressure balloon multi-day flight and where the flight actually went. So the actual flight path is in red, and then green is the standard deviation, and then the green line itself is the most probable trajectory for this multi-day flight. And this flight path was not corrected, so this was all done at the beginning of the 3-day flight. So even before I mentioned 3 days out, weather is accurate, but it's still likely to change. So there's still a significant portion of uncertainty due to even that forecast for this particular work. And what they did, and one of the more sound ways right now to quantify this uncertainty is actually run Monte Carlo simulations, changing things like the inflation fill or parachute drag or things like that, that do play a significant portion in your actual trajectory prediction. So this next slide here that I'm showing now is just an example of how that variation and that uncertainty in running a Monte Carlo simulation can actually inform the people who are doing the mission better about the work and making decisions for the flight itself. So this is the Astra High Altitude Balloon Flight Planner. This is actually a flight if you were to launch this morning from Blacksburg at 8 a.m. It ran 15 simulation flights. And the yellow spots here is where it calculated the balloon to burst for all these different simulations. And then the blue dots is actually where it predicts the landing site for all the different flights. And you can kind of see here, this is just pulled out. So this is another view that they provide in the Astra. It gives you a landing site heat map, which essentially says you have a higher probability of landing in this area and this area, and then there's some probability landing in these other areas around. And so even from if you were flying at 8 a.m. this morning, you can see there's a pretty wide range of where this balloon might land, depending on some very small parameters that were changed and adjusted for these Monte Carlo simulations. So being able to quantify this is the most probable path that the balloon will take is significantly increases the confidence where your balloon will actually fly on the day of the flight and helps recovery for the balloon. So where does that take us? So that was all about the balloons, a little bit about the atmospheric data that it needs and some of the uncertainties. So how does this fit into what I'm doing in the big picture and what we're doing at Virginia Tech? So all of this feeds into what I'm looking at for my dissertation. And the primary objective is to integrate high altitude balloons into Discotech, which is the mission system optimizer. So right now, the work that I'm doing is actually writing these different high altitude balloon simulators and dynamic functions and predictors for each of these balloon types. In addition to that, you can't just write the dynamics, you have to validate the models are accurate. So part of that is validating with actual flight data, which latex balloons are easier to get data for. And then you have the bigger balloon flights, which there are a couple of existing sources to pull flight data from that are kind of used as a benchmark for modeling balloons and checking your validation of your models. And then eventually I would like to evolve them into Monte Carlo simulations so that you can do something like the predicted the most likely path that this balloon will actually take. And then all of that information will be fed into Discotech, which an example of kind of the Discotech methodology is on the right, the optimization methodology. And this all helps propagate the dynamics of the balloon so that you can do these. You can evaluate whether the balloons, where they need to launch from, when they need to launch to be able to have, maybe for some coverage objective for 24 hours, do you need to launch one zero pressure or super pressure balloon? Or if you do it, can you do it with 15 latex balloons? So kind of comparing different missions like that, depending on your actual objective. And then that kind of all leads to what we're doing at Virginia Tech right now. So Kevin Stern and I are actually in early development, but we are working on developing course curriculum for general interest in space, so AOE, ECE, and then potentially other departments, looking at integrating HABs into the classroom. And so offering a way for students to see, you know, fly payloads, you get really incredible images, kind of like the one on the right. And not only that, it's hands-on experience for science that's super relevant, and incredible skills, teamwork, and everything like that, that the students should have by graduation. And it also supports research projects, right? Because it is that near space environment, so you can test new satellite tools. It helps increase the chance of success for CubeSat satellites in the future, so you can test their stuff beforehand, before a CubeSat launch, and things like that. And one thing that's really cool, we're actually going to be doing a launch here probably at the end of April, to help not only develop curriculum and start looking at what payloads we would want to fly for the students, but also using those flights as validation flights for my latex balloon predictor for my dissertation. So that's kind of cool. And like I said, so the image on the right, this is one of the cool things you can do. So this is actually taken during the 2017 solar eclipse. You can see the umbra of the eclipse here. And that's actually another weather balloon. It was about a mile away in distance here. So that's one of the really cool pictures we actually took during those flights. So you can do things like that. You can say, hey, I want to take a picture of another weather balloon. Okay, how do you plan that mission? So those are kind of the things I'm interested in. And eventually, looking back one more step, planning eventually things that, like Google Loon, which sad it got canceled, but that opens the door for many other companies to step in and do work similar to Google Loon, like Worldview, which is offering bigger balloon flights for many different reasons, surveillance, flying and testing payloads, and things like that, offering the balloon side aspect of it, and then offering the customers the available payload space. So that is a very fast introduction into high altitude ballooning for free flying balloons. Do you have any questions?
I have 1,000, but I'm gonna stay quiet because I know where you live and I can bug you offline. This is awesome though. I'm also super excited about this in general and looking forward to the days when we are launching balloons or multiple balloons every semester.
Yeah.
So this is great stuff.
So I have a question for you. I'm just curious. Do you try to revise those probability distributions as, you know, on the day of the flight or after the balloon actually takes off?
Yeah. So that's actually one of the really cool things that doesn't exist yet at Tech, but one of the things that I'm interested in building is actually taking live feed. So from, say, an APRS beacon flying on the balloon, and integrating that into, okay, so now you have its new location, its new altitude, and how it's moving. So if you predict forward, where would it land now? As it's going, is it landing where you originally predicted when it took off? Or is it going to be maybe land in an unsavory place, and we have a cut down mechanism that we're like, okay, cut it quick, so that we can recover it. Like if it's for whatever reason makes it to the Atlantic and we're like, oh no, we don't want to lose it, then we can cut it down before the balloon actually bursts. So yes, you can do that. And there are a lot of companies, so Raven among others, that have things like that built into their GUIs, so that they can make decisions about, especially if the balloon is floating, their landing locations with the larger payloads to make sure that it lands in, you know, farmland instead of over a city or in a lake or in a no-fly zone if it happens to get anywhere close to something like that.
And for the record, that happened a few years back. We launched a balloon from Blacksburg, and it made it all the way to the east of the eastern shore. And we never got that payload back. So it's real concern.
So I actually work on exactly that area. So I'd be very interested with my thousands of questions as well to talk to you about it more. But could you just touch a little bit more on the uncertainty quantification, and what is it, you know, when you go back after the fact, what should the uncertainties tend to dominate? Is it uncertainties in the weather, or is it uncertainties in the drag model? I mean, do you have an idea of where the relevant dominant uncertainty comes from?
So when you have a much higher prediction uncertainty due to the weather model when you start running predictions a week out and 3 days out. If you run 24 and 12 hours out, the uncertainty tends to be dominated by those other aspects of it, your dynamic model, so your thermal model and your thermal predictions, but also like the coefficient of drag is one of the main aspects for all of the balloons, ZeroSuper or even latex. Having an accurate model of that, especially as it goes through the tropopause, is something that can significantly change the actual flight and the actual flight path. So yes, the coefficient of drag is probably one of the bigger places where you see that uncertainty come in from. And a lot of that is just from the shape of the balloon itself. So there's been several different works done recently that may or may not get incorporated simply because of the high computation due to calculating the thing. But one of them was treating the natural shape of the balloon, like the ice cream cone of the balloon, doing something similar and calculating on each point of the balloon, kind of like a finite element model for thermal and also like physical shape stresses and other considerations, so you can have a higher fidelity version so that you reduce some of that uncertainty, especially I believe that was for a zero pressure balloon flight, maybe even the early super pressure balloon flights. And so work is being done to reduce some of that uncertainty that comes into the coefficient of drag. But there's still, at least my incorporation of it into some of these predictions, it will be looked at, but it will probably not be included. The predictions will be good enough because they're historical. Most of the missions would be planned years in advance. And so you might not need the ultra high fidelity precision for the big balloons that you would need if you were preparing for a big balloon flight the day of. But yes, mainly in the coefficient of drag is probably the biggest term of where like the thermal all gets looped in and the payload weight and things like that.
Thank you very much.
Yeah.
Actually, maybe one quick thing to mention. I know I have the problem of constantly offering like 1,000 different payload ideas, all of them usually radio related, but there is an ECE senior design project to design the next version of a CubeSat UHF antenna. And it kind of naturally mates up with the RFM69 type radios. And so maybe as ammunition for you guys, something to think about for the April flight or any other kind of near-term flights is they have a goal of building a prototype by the end of the semester. And so maybe you guys could fly that to, you know, add ammunition to the argument about integration with curriculum and supporting online projects, all that kind of stuff. Basically, copy, but very similar to the antenna flew on PCC CubeSat. It's our own version of it that we can control more and don't have to purchase for, you know, thousands. You know, why buy for thousands of dollars when we can build it for thousands more of dollars with all the testing and stuff we have to do. It's kind of the spirit of it. But yeah, so just maybe keep that in the back of your mind that they're doing that and it should be ready before the end of the semester. I don't know if it'll be ready by April, but
cool. Yeah, we'll definitely have to keep
maybe
that in mind.
even if they finish and move on, the prototype will still be there, and I'm helping them with the test measurements and all that. So I'll probably have access to it if we wanted to fly it anyway. You know, maybe not in April, maybe a future flight.
So I had
sorry, go ahead.
I had a question that sort of relates to Lenny's kind of question. Is there interest in the model that you make on the prediction of getting some kind of like historical type of that? So I guess and then going back and kind of waiting and figuring out what was the best, you know, what was the best prediction type thing?
So one of the things that, one of the ways that you can integrate data, and one of the ways that the example that I showed of the multi-day super pressure balloon flight, one of the things that they actually did for their atmospheric data integration is that they integrated some historical wind data. there's kind of a caveat with that. So when it is in these high variability seasons, you can't trust the data as much. So it's a much lower weight in like the integration scheme that you use for that. But in times, in the winter or in the summer, when your winds are pretty consistent throughout the years, you can use that historical data, you can weight it higher, and kind of use some of that historical data to help bolster your predictions. But yeah, there is that caveat of, well, just to give you an example, so for the 2017 eclipse, we ran historical data for 5 years, because we were like, okay, we want to end up in the path of totality. So where do we need to launch from? What launch sites should we look at? So someone basically went for the last 5 years. This was probably in 2015. So it was, 2010 through 2015. From the date of the eclipse, what would the flight be like in 2017, or what could it be like? And it looked like a star. All 5 years went different directions from this single point. So it was like, okay, our historical data, we can't really integrate it because it doesn't help us do anything. But it did give us an idea that we picked 5 locations, and we kind of had 5 setups for this mission planning that we could contact and say, hey, can we come launch here because the flight prediction winds have us going west during the eclipse, so we're going to need to launch from east of the eclipse. Or in the case that happened is we were on the west side of the eclipse and launched, and it flew east during totality. So this was on during ascent. We were moving east during totality. So we were able to capture a picture like this, which is another weather balloon during totality. So it's just an idea of how you can use historical data to help inform some of your predictions, but you kind of have to use more common sense in terms of it might not always be helpful, like for the eclipse when it kind of did the flower thing for the last 5 years.
Yeah, so, and sorry to dominate anybody else kind of interrupt me, but something, and I'm probably not using the right terms, maybe the idea I'm trying to form is a way to have a prediction, I guess prediction results kind of leading up to help maybe inform of which of those ones is the better one. Does that kind of make sense?
I believe.
So if if your thing was like 5 days out, but then you had a prediction for today, and say you had a balloon, like basically with the idea of like having a bunch of test balloons and figuring out what's going on. And then you can say, well, of these crazy star pattern models, the one that's flying east is working out like this week, and we think it's going to continue to keep doing that.
Yeah.
That's going to make sense?
Yeah, no, I mean, that can definitely help increase your confidence in the flight path for the day that you're planning on launching. There's still going to be some variability, but having kind of ideas or running the simulations 5 days out, 4 days out, 3 days out can be helpful. But there's kind of this question of, what will the weather be? It can change pretty quickly, especially in this region. We don't know what it'll be, but yeah, it certainly wouldn't hurt. And especially so a lot of times for the big balloon flights, they do pilot launches. So they use small balloons with like radiosondes. And so those help them have either collect better data or more accurately see where their balloon might go on the day of the launch. And they'll release those a couple of days in advance too, even to do something similar to that. I've heard of a couple instances of that. So yeah.
Okay. Yeah, there's some more we can talk more later. But. Otherwise, I'll put on my general MC hat. And any other kind of questions on this?
I have a question about you've talked a lot about like pulling data from other sources and incorporating that into the models. Can you talk a little bit about like your access to that data right now? Like I saw there was some global forecast model stuff in there, or global forecast system stuff in there. Like, do you know how to access like the radiosonde data that comes out of National Weather Service, right? They launch I'm sure you know this. I know you know this. The two that get launched twice a day, every day, next door to our building here.
Yeah.
Like, how do you actually get that data? And how do you get that data in a timely way, right? Because I could see that being useful, right? If we wanted to launch from here, 10 a.m. or something, or maybe, I think you can see where I'm going with this. If we had whatever the last Radiosonde launch's flight path was, like 6 hours leading up to our launch or something like that, maybe that would help inform the guests.
Yeah, definitely. So Radiosonde data is actually one of the, besides just the forecast models, is one of the more accurate ways that you can get data that can contribute to your prediction. You still have the spatial, like we're lucky where, it launches next door, so it might be, more accurate for what we would launch for the day of. But in cases where you don't launch radiosondes next door, you still have the spatial and temporal data that you have to consider, or the kind of the offsets for that, and that uncertainty. However, yeah, radiosondes are definitely important. In terms of accessing data, so I've never accessed radiosonde data before, but I have pulled GFS data. And so there is a part of this work that is going to be figuring out how to efficiently access sets of data, either historical sets of data or predictive data for large swaths of land area. So that is something that is going to be investigated soon. I haven't done anything on the scale of multiple balloon flights at the same time, being simulated at the same time.
Okay, cool. Yeah, I'm generally interested in that as well. Just like how, do you download files from some website, or do they have some other API, that kind of thing?
Yeah.
What are the file formats? All that kind of minutia of detail. I'm interested in as well.
Okay. We can, when I start getting into like trying to set it up to pull all the data, I'll loop you in on that.
Cool. Thank you.
So I would be interested as well. I'm curious, when you look at the historical data, do you look at historical observations, or do you use something like the reanalysis? Do you know what the INSEP or ECWF reanalysis? Yep.
Yeah, right now it's been primarily just observations. So like the actual recorded historical data, and then using that for the historical predictions, or predictions based on historical data. I actually haven't heard of this reanalysis.
So okay, well, I'm happy to talk to you about that. In fact, for what you're doing, I would probably recommend that you stay with the actual data, but I have a lot of friends who do the reanalysis, both in the European Center and at INSEP and at JMA. They go back and they run all the data again, and get sort of a continuous gridded, very, very pretty, but not always accurate estimate of what today's model would have said the weather was.
Okay.
So like the analysis is the current estimate, the reanalysis to go back and do it with today's model in the past.
Okay.
But it's exactly what you're doing, which is where I think the complaints that I make about the reanalysis show up really, really clearly.
Yeah, there's a lot of work being done right now, just even how to interpret the data and different ways to weight different types of data, radiosonde data, historical observation data versus prediction data. And yeah, there have been a couple of interesting reads actually published in the last 5 years about different ways to start handling that data in order to look for this, mission optimization, quantifying uncertainty. How do you even quantify the uncertainty coming from the prediction itself, which is a large portion of the uncertainty in the prediction. So, or
do you really want to weight it at all, or do you want to look at the different trajectories that come out under different realizations and then see on the day what it looked like is happening? Do you use the European Center for medium range weather forecasting? Do you use their forecast at all, or just INSEP?
Yeah, mainly just the NOAA stuff with the GFS right now. So no.
From an operational point of view, the ECMWF forecasts are really good.
Okay. I'm more familiar with GFS because I'm more familiar with like the public prediction tools that are available right now for especially latex balloons, and most of them just use GFS. And occasionally like the rapid refresh, which is just over the US. So I haven't heard of that, but I will make a note of that.
Yeah, I'm happy to talk to you about it. As an American who was working in England, I sort of got to see the insides of both the NOAA and the European systems. So there's a lot of good information. It's good to use both if you can get them in time. And you should be able to get them for free.
Sweet. Thank you.
Okay, any other, maybe I'll just say one final question here as we're getting close to our time for the end of the hour.
Let's make a last quick comment. Again, I think this is awesome. I really like that idea about the continuous prediction stuff, like taking real-time data and updating your burst and impact estimates. And so on that note, there's stuff in it. If I get all the wishes that I wish for in terms of like ground station networks and integrating how we pull data from balloons and satellites and all that kind of stuff, there are servers that we have access to that we could, think about building into this kind of ballooning platform, ballooning network that could run that kind of thing for you and produce those results and push them back to you. So it's not just running on a laptop somewhere, kind of ad hoc. It could be a centralized thing that could be distributed out to everybody. So like if we have chasers and stuff in the field. So if you need servers or better compute resources, let me know, because I would count this as ground station work generally, as ground stations are more than just for balloons. It's the ground infrastructure to support this kind of stuff. So
yeah,
we can make that work.
Cool. Thanks, Zach.
Yeah, thank you. This is awesome.
Okay. Well, thank you for everybody for joining. And we'll have another seminar here in 2 weeks with the RockSat team. So thanks again for joining, and thank you, Jenny, for the wonderful presentation. Everybody take care and have a great day.